Alright, so today we are talking about the types of intermolecular forces, and we're going to put them in order of strength along with the types of bonds that we already know once we get all the way through the different types that we have. What we're going to start with is just looking at this word, intermolecular forces, a little bit closer so that we can break down what that word actually means. We can take all forces between molecules or inside molecules and divide them into two categories. One being intramolecular forces, which are those that are inside a molecule. And those would be the bonds, or the different types of bonds that we've been learning about so far. Intra is a prefix that means within. When you go to college, a lot of times colleges will have called intramural sports. Have you heard of this? Yes? No? When you play intramural sports, who do you play? Do you play other colleges? No, you just play other people at your same college, so that would be within your school. Intramurals are within your school. Intramolecular forces are the forces that are inside the molecule, and we've been calling those bonds. What we're going to add to that today are intermolecular forces. Notice that the spelling is different. Inter is a prefix that means between. So when we talk about intermolecular forces, we're talking about the attractions between molecules. So the forces that hold molecules next to each other, not that hold the molecule together. This is kind of like when you talk about an international flight. It goes between countries. So inter means between. The strength of those intermolecular forces is what determines the phase or the state of the substance. Whether something is a solid, a liquid, or a gas is determined by the intermolecular forces. And if you want to change the phase from a solid to a liquid or to a gas, you have to overcome, almost like you have to break those intermolecular forces. There are three kinds of intermolecular forces that we're going to go over today. And we're going to start with the weakest one. The weakest kind of intermolecular force is called a London dispersion force. Yesterday, when we talked about electronegativities and we talked about types of bonds, we talked about how the electrons don't necessarily have to be shared right down the middle in between atoms. They might be more on one side or more on the other side. London dispersion forces are thought to be caused by the movement of electrons. And these are the only attractions that you have between nonpolar molecules. electrons are constantly in motion inside an atom, and it's pretty much a random motion. So occasionally, somewhat randomly, it's possible that you might get all the electrons gathered on one side of the molecule and not on the other side. And that would create a charge on that one side, just like we talked about yesterday with the types of bonds. But it doesn't last very long because electrons are always in motion. So we call that charge a temporary dipole. Di usually means two. Pole, of course, means polars, like a plus end or a minus end. So a temporary dipole is a split second where the electrons have all ended up on one side, and they cause a negative charge on that side, and then a positive charge on the remaining side. So for a split second, you have a molecule that has a slightly minus end and a slightly positive end. The larger the molecule that this happens with, the more electrons are going to be involved. That means you get a stronger attraction from it. We can use this idea to explain why fluorine, chlorine, bromine, and iodine are gases at standard temperature and pressure. All of those are diatomic elements, which means when you find them in nature, you find them in pairs. So it'd be F2, Cl2, Br2, and I2. We should know from yesterday that things like Cl2 are nonpolar. So the only intermolecular forces they would have would be London dispersion forces. And because there's only two atoms involved, they're also relatively small molecules. So if they're small and they're nonpolar, there aren't very many forces, or not very much strength to the forces that hold the molecules side by side. And if there's not very much strength to hold them side by side, they don't stay side by side. They spread out. And if they spread out, what phase do you get? Not a solid, a gas. So looking at the types of forces that are available to hold molecules side by side can be used to explain why certain things are gases, why others are liquids, and so on. If you had a larger molecule, though, you might be able to get a liquid or a solid. Something like oil, like gasoline, those are much larger molecules. So even though they're nonpolar, it's still possible to get liquids. Many of them are liquids, and some are even solids. Things like fats and oils that you'd use in your kitchen are nonpolar, but most of them are liquids and solids. Force type number 2. This is the next strongest. These are called dipole forces. Again, di means two, pole means like a plus end and a minus end. So forces that occur when you have a dipole, or a plus side of the molecule and a minus side of the molecule. Which should lead you to the thought that these only occur between polar molecules. Because to have dipole forces, you have to have a positive side and a negative side. we say that these forces are caused by electrostatic attraction. That's just a fancy way of saying one side is negative, one side is positive, and opposites attract. Of course, you would have the positive side of one molecule being attracted to the negative side of another molecule. So if we take a minute to look at an example here, we can compare the two types of forces with these two molecules. CH4 is methane. That's the gas that we use, or the main gas that we use in our burners. And of course, H2O, water. Hopefully we know that. Methane is a gas. Water is usually a liquid. But both molecules are about the same size. If you did the molar mass for methane, what would you get approximately? Carbon is 12. About 16. Each hydrogen is about 1, so you get about 16. Do you remember what's the molar mass for water? 18. Give or take a little bit approximately. 16 and 18 aren't that different. The size of these molecules is about the same. So what causes the difference? What makes one of them a liquid and the other one a gas? That has to do with the forces that they have. Methane is nonpolar. You'd be able to figure out that it's nonpolar. You could do the electronegativity difference like we did yesterday. And then you'd have to check symmetry. If you drew this out and checked the symmetry, you would notice that it is symmetrical on all sides. You might remember our example CCl4 from yesterday. It's very similar to this one. So because it's nonpolar, the molecules are only held side by London dispersion forces. Those forces are temporary and they're weak. Water, on the other hand, is polar, and its molecules are held together by dipole forces. Those are more permanent, and they're also stronger. Because the dipole forces are permanent and stronger, the molecules are held closer together, side by side, so water is a liquid. That's pretty important. If we didn't have liquid water on our planet, there's a lot smaller chance that we'd have life on our planet. That's why it's such a big deal when you hear in the news that they're talking about whether or not they found, evidence of water on Mars, or evidence of ice on Mars. If you don't have liquid water, you probably don't have life as we know it. So pretty much our whole world depends on water having dipole forces. I didn't think you learned that in chemistry this morning. Okay, one last kind of intermolecular force. And this is a special kind of a dipole force. It's called a hydrogen bond. It's not really a bond. It's still an intermolecular force, but it's the strongest force that we have. So we kind of nickname it a bond, I guess. We call it a hydrogen bond even though it's not actually a bond. Maybe it would be too much of a mouthful to say hydrogen intermolecular forces. It'd be a lot easier just to say hydrogen bonds. Hydrogen bonds are a special kind of very strong dipole. Even though this is the strongest kind of intermolecular force we have, and it's a very strong dipole, it's still only 5% of the strength of a covalent bond. So it's still an intermolecular force. It's still much, much weaker than a bond within a molecule. But it's the strongest intermolecular force that we have. Hydrogen bonds work exactly the same as dipoles do. You would have a molecule with a plus end and a minus end, which would be attracted to the next molecule over with a plus end and a minus end. It works the same as a dipole. The only difference is that plus and that minus are a lot stronger plus and minus than just with a regular dipole. So it's almost like saying you've got a stronger magnet. It's got a stronger attraction or a stronger pull, because you have a much bigger difference between the positive end and the negative end. It only occurs with molecules where you have hydrogen bonded directly to a fluorine, hydrogen directly to an oxygen, or hydrogen directly to a nitrogen. And the reason is because those three elements are very electronegative. So when you subtract your electronegativity difference, it's a pretty big difference compared to everything else. That means the electrons are very much on one side as opposed to the other. You get a bigger plus and a bigger minus. That makes a stronger attraction, almost like a stronger magnet. So even though we talked about water having dipole forces, water in fact has hydrogen bonds. That's that special kind of dipole force. And it's really strong compared to the other dipole forces. That's what gives water its very high boiling point. Most other things its size have a lower boiling point. It gives water some of its surface tension. It allows it to make 6-pointed snowflakes based on the structure of water. Okay, last thing. We're going to do kind of like a little concept map, brainweb thing, where we're categorizing all the different kinds of forces that we know of. So right at the bottom of your page, you've got kind of a title to start from. We said that all forces could be divided into two categories. Intermolecular forces, and what was the other one? Intramolecular forces. if we start with intermolecular forces, what was the first kind that we talked about? The weakest ones. London dispersion forces. You can just call them London forces for short if you'd like to do that. Then we talked about dipole forces. A little bit stronger, more permanent than London forces. And then we talked about a special kind of dipole called hydrogen bonds. The strongest of the intermolecular forces. They work almost like a magnet. If we move over to the other side and talk about intramolecular forces, we had covalent bonds, and then yesterday we divided covalent bonds into two categories. Remember what they were? Polar and nonpolar. So nonpolar covalent and polar covalent. And what major type of bonding are we missing yet? Ionic, the ones we started with. And you might have noticed that I've got these numbered 1 through 6. Those go in order of strength. So number 1 is the weakest, and number 6 is the strongest kind of force.